This episode was made possible by the trainings vertical of the Science Talk and also the QuanTour project. Hello. Welcome to yet another smashing episode of Under the Microscope, where we spotlight materials and nanoscience. And through the science, of course, spotlight materials and nanoscientists. If you're new here, welcome to Under the Microscope. You have made the best decision to follow this podcast or subscribe to our YouTube channel, if that's what you're doing, if you're watching, or if you're listening. So, welcome to the thriving community of more than 10,000 people across social media platforms. If you're an oldie but a goodie, well, welcome back. Thank you for your continued support on all the different platforms that Under the Microscope is available on. Under the Microscope is the only podcast in the world focusing on materials and nanoscience, which is independent and also is in its 6th season, has more than 200 episodes featuring scientists from 20 different countries across the world. If you are new here, I told you, you made the best decision by following Under the Microscope on your podcast app or subscribing to the Science Talks YouTube channel. Today's episode, which is episode number 221, this is a very special episode for me because I got the chance to sit down in person in a studio, and this was a wonderful, wonderful experience. The Science Talk is the official science communication partner of QuanTour project, funded by the German Physical Society, DPG, and QuanTour, together with a lot of other initiatives, is also part of the Quantum Science and Technology Year 2025, which is going to be this grand celebration. In today's episode, we sit down at the Autonomous University of Madrid in Spain, where Carlos shares with us the fascinating world of hot single photons for quantum communication. He explains his groundbreaking research on different quantum materials, especially hexagonal boron nitride, and its promising applications at room temperature. We also dive into Carlos's journey in the scientific community, his international collaborations, and his thoughts on the future of quantum photonics. Tune in as we explore the nuances between hot and cold single photons, their significance in quantum communication, and a peek into the vibrant scientific life in Madrid. So, without further ado, let's get started.
But first, a quick word from our sponsor.
As you know, Under the Microscope is the flagship podcast of the Science Talk. In addition to creating innovative and engaging content, the Science Talk also offers science communication trainings. And one such training is Ace Your LinkedIn as a scientist. This training is designed to teach you everything you need to know about acing your presence on LinkedIn. As a scientist, that is very, very important. As a scientist, this LinkedIn training will give you all the tools and tips to get started with your LinkedIn presence immediately. You'll get hands-on demonstration of the different features, profile optimization, hacking the algorithm, content crafting, engaging with your audience, and also growing your network on LinkedIn. So establishing your brand basically on LinkedIn as a scientist in that training that is called Ace Your LinkedIn as a Scientist. The next batch of Ace Your LinkedIn as a Scientist is in September 2024. More details are in the show notes or in the description, depending on where you're listening or watching. All right, on to today's episode.
Hi everyone, my name is Pranoti. I'm your host of Under the Microscope, and today we have a very special guest. And as you can see, the whole shebang, I'm recording in a proper studio. And today I'm in Madrid to introduce the fourth Carlos Anton Solanas, who is a tenure-track talent attraction for the region of Madrid. And we are sitting at the Autonomous University of Madrid in Spain. Hi, Carlos. How are you?
I'm fine and fantastic to be here with you today. We waited a long time until meeting each other, and I hope that you're having a great time in Madrid.
I am. It's amazing. And before we start with the podcast and talking about the research itself, let's explain a bit to especially our YouTube audience. What is this? Do you want to tell people what this is?
This is a very special case that is traveling around Europe, containing a special sample, a semiconductor material sample that is capable of emitting single photons. And basically, what we are doing in this activity is to tour this cage in 12 different labs located around Europe and measuring in each of them, demonstrating that the emission from this sample is indeed composed by single photons. So it is our turn now, as we are the fourth destination, and we are on it. I am surrounded by an amazing team of students that are helping me to do. Also, developing this kind of outreach activities is also great. So we are having a lot of fun, and in particular now as well. So super happy to be part of this QuanTour activity.
That's wonderful. And so we have had, of course, some of the QuanTour heroes already on the podcast and talking about quantum communication from the theoretical point of view, from the experimental point of view. And today, if I remember it correctly, you're going to tell us about hot single photons for quantum communication. Hot single photons, not the hot probably that people are aware of, but they are still hot single photons. So let's start with understanding your research, right? Please explain your research to me in super simple words.
Okay, to say it in some simple form, I'm basically studying different kind of materials that can be applied for photonic applications. And in the plethora of photonic applications, I'm more focused in those that involve very little amount of photons, single photons in particular. In order to do that, you can investigate different kinds of materials that will offer different properties. For certain applications, you will require materials that need to be operated at cryogenic temperatures when you want to have very high quality single photons. And for other applications, more forgiving, you might have materials that can be operated at room temperature and so emit single photons in much more comfortable conditions. So to say, you don't need cryostats, which are basically very complicated fridges where you can cool down your sample close to 0 Kelvin, right? And basically, this is the kind of research that I do, investigating novel quantum materials with the scope of utilizing that quantum emission for photonic applications, so to say.
Just to recap, right? With Armando, who was in Austria, he was making relaxed quantum dots. Then Ronaldo in Rome, he was making stressed quantum dots, and he was using different kinds of stress to align the quantum dots to a certain axis. Now, considering that is how much I know about the quantum communication and the QuanTour project from the science perspective, what are you doing? Because you already mentioned you're doing like the room temperature measurements. I guess that's what you mean with hot.
Yes, exactly. Both Rinaldo and Armando, they're studying semiconductor quantum dots. This is the kind of material that is also used in this activity of the QuanTour. At the moment, even though I am trying to investigate different lines of research, I'm not particularly focused on semiconductor quantum dots, but in defects in hexagonal boron nitride, where you can also form some sort of quantum dot, even though it's not really a quantum dot as we understand, we physicists. It's just a place where one atom is vacant, is missing, and so you can still have one electron confined that can spontaneously decay and emit a single photon.
Right.
It's a different way of forming a quantum dot, but that can survive at room temperature. Something that is not possible in principle with semiconductor quantum dots, where you will require these super cold temperatures.
And for the QuanTour source, we need the cryo temperature, right?
Yeah,
That's
this is challenging.
Cold single photon.
Exactly. And maybe it's also interesting to explain what is the difference between these hot and cold single photons or samples, so to say. Basically, when you are cooling down your sample, you are making the environment of your material be cleaner. You can associate temperature to vibrations. So if you decrease the temperature a lot, your material stops vibrating.
So it's stable.
It's stable, it's calmer. It's like playing a violin in the street or in a place like here, right? So basically, when you are cooling down your sample, you will be able to emit a single photon, which is a better tune of a music, so to say, something cleaner, something nicer. And something that in particular for quantum applications, it is very important because in general, most of the photonic applications require to interfere single photons. In order to interfere those single photons, you need them to be identical or you need them to be noiseless. And this is something that you only reach at cryogenic that do not require photonic interference and that still you can get this kind of emission and have a very good application in our, so to say. You can think of putting it in a plane, in a drone, in a car, or in a satellite. where in principle it's much more difficult to have a cryogenic system where you can get this ultra cold temperature.
Okay, this is super fascinating. Now tell me, you mentioned boron nitride, right? Boron nitride and a defect in boron nitride, and the hexagonal boron nitride
Yes.
you mentioned, and that has the hexagonal, that means 6 atoms in the lattice, and only one of them is missing or 2 missing, or what do you define defect?
This is a very complicated question. Basically, you have, as you said, your hexagonal lattice with borons and carbons displayed in this hexagonal arrangement. And then the kind of backhands that you can have in order to confine one electron, it's a very complicated research that is taking the time of many physicists at the moment to understand what kind of vacancy you can form, and so what kind of emitter you will have. In general, it could be carbon vacancies, the ones that are more famous, so to say, that you can generate in different manners. But if you ask me, if we go now to the lab and we see this single photon emission emitted from my material, HBN, and you ask me what kind of vacant is this one?
That you won't be able to...
Yeah.
Okay.
But as long as it emits single photons.
I completely understand. I have so many questions, and I feel like I can just do the entire podcast just talking about your research. But I'm going to continue asking a few more questions, right? Very simple, so to say, question. Simple from my perspective, probably difficult from your perspective to answer. There are 2 kinds, right? So Armando and Ronaldo, their quantum dots are like single photon emission. In their cases, requires the cryo, similar to the Q source here, or the Q torch as we call it. And in your case, these are the hot single photons that are like the hot meaning at the room temperature. Now this hexagonal boron nitride that you mentioned, that emits single photons at room temperature, is it better or worse when you cool it down to cryo temperatures? Have you tried that?
Yeah, there are also, not in my case, I didn't have yet the time to start this line of research at cryogenic temperatures with HBN. But there are some other groups. It comes to my mind, for example, the group of Aymeric Deltail in Versailles, in France, that has been doing experiments at 4-7 Kelvin or so, where he have seen very good performance of this material as well at cryogenic temperatures, and recovering the properties that you will have as well with semiconductor quantum dots. So in principle, yeah, I mean, you just have to cool down the sample in order to get a proper single photon again. It is just that it makes things simpler if you can just enter your lab and just start working on your sample without needing to cool everything down and depend on many other systems. As a starting activity in my tenure track, it's very convenient, and also for the students as well. You can ask a PhD student what do they prefer, to be operating a cryostat or just enter directly and start to do experiments, right?
Yeah, absolutely. It also saves resources, right? Because for the cryo measurement, it's not just the setup, but you also need the helium gas.
You will need 2 things, either a liquid helium, which luckily we have in this university, and you just make your liquid helium pass through your cryostat and then cool down the temperature.
Correct.
Or you will need some sort of fridge that is also operated with helium, in which you have a closed cycle, like a thermodynamic cycle that is cooling constantly your sample. Then, I mean, it's for sure easier to use, and also it consumes less energy, right? This is a green sample, if you want to call it like that. But yeah, this is basically the difference. It's easy to use, comfortable to use.
Absolutely.
And providing good physics as well.
So now let me ask you from the material perspective, because I'm a material scientist, right? And I did do quite a bit of hexagonal boron nitride exfoliation. So do you also produce hexagonal boron nitride, or you buy, or you collaborate with groups who create it? Like, how does that work?
The kind of HBN that we are using, it can be bought commercially. So it's very easy to get a batch of this material to use it as long as you want. And then I also rely on many collaborations in Europe, and I think this is fantastic because it keeps you connected with the community, and it's much quicker to advance producing results, so to say. For the generation of single photons with HBN, there will be different ways of creating these defects. It would be in nanocrystals, where they can be generated spontaneously by heating up the sample up to 1000 degrees. Then these atoms spontaneously disappear, and then you create a vacant. Or in few layer HBN, you can also irradiate with electrons.
You're actually introducing the defects.
Where you want.
You might be getting like the perfect hexagonal boron nitride, either bought or from your collaborators, and what you're doing is we're basically destroying it.
No, destroying it. Precisely. You irradiate it, and then you know perfectly where it's going to be, and on top of it, it's quite reproducible where the wavelength of the emission of the single photon will be. So it's quite versatile, and it takes not much time to prepare the...
Yeah, if you just have to destroy it, then it's fine. Yeah, no, I'm kidding. You mentioned the way you introduce the defects is, of course, with the electron beam and irradiation with a laser or something, or heating it up. Sorry,
Yeah,
and heating it up,
heating it up
right?
in an oven, and then you will not know where they are and which wavelength they have. And then via irradiation with electrons, you will know where the wavelength is and where it is located.
And then last two questions about your research, and then we'll move on, I promise. The first question that comes to Armando, so with Armando and with Ronaldo, we got a feeling for the dimension of the quantum dot. So it was something like 5 to 7 nanometer in height and 15 to 30 nanometers, something like that, in width, because they were like bumps. Can you give us an example of what is the size of this boron nitride? Is it because it's a 2D material, right? It's not a 3D structure as such.
Yes and no. When you are generating these defects, you start with few layer HBN, so it does not require to be in the two-dimensional space. If you simulate the orbital of the electron, I have the impression that it would be even smaller of a semiconductor quantum dot.
Right.
Because a semiconductor quantum dot is rather big, right? 50 nanometers diameter.
Big for
Yeah.
a quantum dot, so to say.
And
or,
then
yeah.
around 7 nanometers height.
In
right?
height, yeah.
Here we will be talking about the one atom that is missing, right? So
The sample that you have, that you put to emit the single photon, is this like a flake? Is it like a powder?
yeah. If it's
Yeah.
a flake, if we prepare a flake and then we irradiate it, the flake will be probably on the order of 20 by 30 microns.
Okay.
And then we irradiate it in specific locations that we can find easily.
Mhm.
If it's nanocrystals, they can be very little. It can be in the order of 1 micron or less.
Wow.
And they are scattered on the sample. So we have to
Right.
look for them very carefully.
And then there would be a single photon from multiple different positions, hopefully where you have introduced the defects.
Precisely,
Right?
yeah. Where you
Okay.
have these nanocrystals, some of them will be optically active, so you will have photoluminescence from them.
Mhm.
Some others will not. It's basically, in the case that you have nanocrystals with random defects, it's about looking for them, which is a bit annoying. So we have developed techniques to scan for them. And if it's in this micrometric flake, then it's quite easier because you know where you have irradiated, you know
Right.
where you have to go,
Right.
and then it's basically easier to find.
Okay. Then the last question on your research, and then as I promised, we will move on. Important, of course, to have the quantum communication in the real life, like to implement that in real life. And hexagonal boron nitride is one material. Are there other materials which also are good at emitting the single photons in the hot temperatures? Hot in this case, meaning, of course, room temperature.
As famous as HBN, I would say no. At the moment, with the current investigation that there is in the community, I think that HBN is the more forefront room temperature material that you can think of. And then surely you can find others in which this exciton can survive at room temperature, but always paying the price of having a single photon that contains more noise, so to say. And because it's the last question about my research, and I would like to complete a little bit. It's not only that I'm doing research on HBN, I'm also researching on semiconductor quantum dots, keeping collaborations with other researchers, some of them within the QuanTour as well. The main activity at the moment here in Madrid is indeed HBN, but I try to keep my options as wide as possible in terms of quantum materials because they all offer many different properties, different experiments, and different applications. So I have been studying for a really long time semiconductor quantum dots. They are a super fun platform. You can study super top-notch physics. And I hope to continue studying, investigating them.
Of course, we are not favoring any material here. It's just like multiple different things that you're doing. And you also mentioned that you are working with other, like some of the groups also in the QuanTour project, right? Is this related to then the COMPHORT project that you were telling me about earlier? Do you want to talk a little bit about that while we're talking about your research?
Talking about HBN, we recently obtained a QuanTerra project, which is a special type of project in the European Union, where you have to form a consortium conformed by different academic partners and also industrial partners. In this QuanTerra project that we started just 1st of July, the motto is to investigate quantum communications with single photon sources that operate at room temperature, HBN. And the partners, the one that is belonging to the QuanTour is one of the organizers.
Whose group created the QTorch, the source?
Yeah, he's an expert in quantum optics in the solid state, and in particular, he knows very well the techniques on different quantum communication protocols, in particular with what we call quantum key distribution.
Mhm.
He is one of the key players of the consortium in order to implement finally the application with these hot single photons. So send them from emitter to receiver, encoding a message in these single photons, and then transfer a message securely.
That's something that Toby did mention in his episode. They're doing this like the live testing or like real life testing. It's 70 kilometers apart, the cities are, to do the
transfer of a message. I guess that I didn't watch his podcast, but I guess he was referring to fiber communication. So the light was sent by fiber or in free space. If it's 70 kilometers, I guess it was via telecom fibers.
Yeah, it's probably with the net something.
In our case, the transfer of these single photons will happen in free space. So in the air.
And what is the distance?
Not so long. It is not so far away. So it's 100 meters, what we have promised. Let's see.
700 meters, but that's really good.
Yeah, the idea is to do this in the campus of the Technische Universität in Berlin, where Toby is.
This will happen over the course of the project, probably. And it just started, right?
I hope 2027. Yeah, this is what we promised.
I want to be there recording, like when this experiment is happening at the campus with the 700 meters distance.
I hope we're going to be at that point.
This brings us even closer to the real life application where we can actually use the secure communication with the quantum communication, right?
Yeah, I think it's a great effort that we are trying to do this kind of activities in Europe. At the same time, we have to look around at the world scale and see what is being implemented at the moment in other places. And I am obliged to say that China at the moment is leading on this quantum communication protocol. They have already done it with satellites. And I also had the chance to be recently in Singapore, and I saw a startup there that is implementing also this kind of technology to be launched in the space. We have to, so to say, kick our asses here in Europe to try to catch up with what is done in other places in the world.
Yeah, definitely. And it's also good to have this like a perspective, like zooming out a bit and also looking at, it's good to have scientists like you who have, like you are in it, but you also have the global perspective, because that is something that is very important and oftentimes missing, because very often it's very easy to get lost in your own lab, in your own research. So this is very good. What is the QuanTour, was it? What is that? You mentioned this is like a European-wide thing, and COMPHORT is one of the consortia. What is QuanTour? Is it like...
Yeah, it's an initiative of the Horizon 2020, if I'm not mistaken. And then the program for funding is a little bit different of what it would be the standard European Research Council. In QuanTour, you apply with a given consortium, and then each country is the one that in the end will fund the activity of each partner. It has the European flag, but in the end, it's some sort of international collaboration within the funds of your agency, of your own country. And it's an initiative that, if I'm not mistaken, it was started. This is the third round of QuanTour. So we were very lucky to get this project selected in the modality of applied quantum physics. Let's see how it goes. We are having the kickoff in September to meet all the partners. And then at the end of September, I will have to go to Amsterdam, where we are meeting all the consortia. We will be gathering to see how it's going and to exchange our starting within the project. And
I'm going to ask you more question about that after we stop recording, but this is super interesting. I want to know more about it, because just last year I was also in the Amsterdam area and there are some really cool things happening there. We are about to take a short break, but stay tuned, because when we return, we will dive deep into the career journey of our guest today. It is always inspiring to see the paths that lead scientists to where they are now. Don't miss it. I hope you're enjoying this episode of Under the Microscope. I'm your host, Pranoti, and I absolutely love bringing you these conversations with the brilliant minds in the field of materials and nanoscience. It's incredible to hear about their research, their journeys, and their dreams for the future. At the Science Talk, through our flagship podcast that is Under the Microscope, our vision is very simple. We want to bridge the gap between the scientist and the public. We believe that platforms like this podcast can create a space where scientists can share their stories, challenge stereotypes, and inspire others with their passion and experiences. If you're enjoying these deep dives into the world of materials and nanoscience, I would love for you to consider supporting us by becoming a patron. Your support means the world to us. It helps us keep the podcast running, improve the quality, and reach even more curious minds such as you. As a patron,
you will get some awesome perks like early access to the episodes, behind the scenes content, and even special shout outs on the show. Plus, you will be joining a wonderful community of science enthusiasts who believe in the power of sharing knowledge. So if you're up for it, head over to patreon.com/the science talk and see how you can get involved. Every little bit helps, and we are so grateful for your support. Thank you for being part of our mission to make science more accessible and engaging for everyone. Please follow the link in the description, in the show notes, on Spotify, or wherever you're listening to this or watching this on YouTube. Do consider being our patron. Thank you for listening. Thank you for watching. And let's get back to the episode.
Tell me a bit about your career journey. How did this happen? Like, how did you get to where you are today, let's say, sitting here?
I did my studies in Madrid, here in this university, my master and thesis as well, but in a different topic, not so much in quantum photonics, but it was more in nonlinear photonics, as well related to semiconductor materials. And then during my PhD, I had the chance to do a 6-month internship to go to work in the group of Pascal Senelart, which is the next one in the, I shouldn't say
You're
anything.
not saying, no, it's fine. It's okay. It's okay. If people are watching and if people are listening and they already, it's all public knowledge, of course, with the QuanTour.
Then I went there for this internship and she offered me to stay there for a postdoc, which is what I did. I finished my PhD here and then I went to work with her. Within the first year, I was very lucky to obtain a Marie Curie fellowship.
Nice.
So that enlarged my stay in her group. This was, by the way, since 2015 that I started my postdoc with her until 2019. And then after these 4 years and something, I decided to change a bit the type of research that I was doing because it was very focused on semiconductor quantum dots. I was doing great physics. I was having super nice publications and collaborations. But I decided to change the material platform. And I decided to go to Germany to work on 2D materials with one of the experts in the field, with Professor Christian Schneider, where I have been working with for 2 years and a half. Initially, first in Würzburg in 2020. And then mid-2020 till 2022, we were working in Oldenburg.
Oldenburg, okay.
Yeah,
During
North
the
Germany.
pandemic, it was.
The moving was in June 2020. We found the university empty.
Oh, wow.
It was a very strange time, but for some strange reasons, it was the most productive time in our lives for something that I cannot really explain, because for some other people, it was completely the opposite. So it was a very fun moment, getting very new results using these 2D materials, knowing many other properties about quantum materials. And then in 2022, I was starting to feel like I had spent too much time abroad. In total, I think if you sum up everything, it's 8 years abroad.
That's quite a lot.
I think it's becoming the standards now for postdocs. No, it's not really true. But it was really long, and I had the chance to be back in Spain, and then I started to apply, and I have the opportunity with this Atracción de Talento, and here I am. I am on a tenure-track at the moment, trying to keep my network of collaborations in Europe, and this initiative is also an opportunity to do. And just trying to get to know to the students of the faculty, form my group, and do cool physics. That's it.
That sounds really cool. And also the international experience, and also changing your research focus a little bit, not stopping, of course, the semiconductor quantum dots, but also like the semiconductor materials, but also adding to it. I think that's what happens, right? The further you go in your career as a scientist, the wider your research scope can get.
Yeah, this is something that my PhD advisor, Professor Luis Viña, he recommended me to do for this internship during my PhD. He advised me to change the topic of what I was doing during my PhD to explore something else. And at the beginning, I was very scared, but it turned out to be one of the greatest that I ever had in my professional career.
Right.
And I think that changing physical platform is very important when you're shifting from PhD to postdoc, and also maybe sometimes between postdocs. But the shift has to be also clever. Doesn't make any sense that suddenly I'm doing quantum optics and then I'm gonna do, I don't know, astrophysics. Maybe it could work for some very clever people, but could be too risky. But a bit of change, I think, is necessary.
Yeah, absolutely. And that's also, I also heard the same thing, right? After my master's, and also when I was thinking about doing a PhD, it was similar. Or when after PhD, when I was contemplating if I want to do a postdoc or not. So I was also advised to either change the material or the techniques that I use for the characterization or application or whatsoever don't change the material and characterization, like the everything else. Because I'm a material scientist, for me, the advice was more like that. So, but it sounds very similar.
Yeah.
That change a little bit, but it's like the calculated risk, so to say, that you take.
Also, very nice for me was to change country, right? In the end, it's just Europe.
Yeah.
So you are always close to your home. It's not like going to, I don't know, the States or Australia or, I don't know, China or any other place where you are really, real far away. But getting to know the different communities within each country, it has been so positive. And now these contacts remain, right?
Yeah.
So if you are thinking of going back to your country to establish your group, I think that nowadays is more required than ever to have pretty good international experience, get to know different communities, that they know you as well.
Yes.
And that so like in this way you can form these networks of collaboration. I think it's very important.
It's very important. I agree. I couldn't agree more. And it's also good to know that even you are still working with the groups, you're still collaborating with the groups
Absolutely.
that you worked at or you were exposed to. That is the heart of science, right? The collaboration and working together. So that's fantastic. It also sounds to me, Carlos, that you have been involved in a lot of interesting research projects. A lot. It sounds like already from the research that you're doing right now, it's very interesting. And now the question I'm going to ask you, I usually get a lot of flack for this question because I put the guest on the spot and being like, if you have to pick one research project that you're most proud of or the most fun or quirky one, could you pick one and explain it to us in the section we call In Other Words? Don't hate me.
This question is like, who you love more, mom or dad?
Exactly. But you all, like today, let's put it that way. Like today, at the time of recording, in this moment, who do you love most? Your mom or your dad or your brother, your sister, whatsoever? Depending on the interactions you have had. What do you feel like? That's why I said, I get a lot of like, how can you ask me to choose between my kids? And I'm like,
my criteria of choosing is gonna be according to how much I learned while we were getting the data and then understanding the data. Okay.
there is no disclaimer, yeah? You don't have to explain yourself. It's fine. You can just choose.
Okay, so it was an experiment that I was doing at the end of my postdoc in the group of Pascal and Lart with semiconductor quantum dots. And I think it's fine if I say the experiment came out of a mistake or just because we were trying different things and we were not understanding very well what we were doing. And what we were doing basically, if I can explain in simple words, is to excite twice with two close pulses a semiconductor quantum dot.
Okay.
So basically, a semiconductor quantum dot, you can understand it like an atom that can be excited or in the ground state. And these two pulses that they were coming very close after each other, they were making the atom excite and de-excite, while at the same time they were emitting photons. Okay, so in the end, we were creating some sort of entangled state using vacuum, no light, and single photons. Okay.
Quantum entanglement, we talked about that a bit. Okay, sorry, go on. Yes.
So we had to collaborate with a very close friend, collaborator at that time, Stephen Vine, who we were explaining to him what we were doing, and he came to us and he said, "But guys, I think you are creating an entangled state. It's this state, a 0, 0 plus 1, 1 state." And we were like, "What? No, it's not possible. Are you sure?" He was saying, "No, you have to do this measurement, and probably then you will see what it comes out." And we completed that measurement. We analyzed the data. It took us more than a year. It was during the pandemic. It was 2020 when we were doing all the analysis. And in the end, it turned out to be very cool physics, extremely simple in terms of how we were exciting the sample and what kind of a state we were generating. Simple at the level that we were surprised that nobody was paying attention to this kind of experiment before. And it has started other experiments that I have done with other groups in Europe, such as, for example, the group of Anna Protasiewicz in Stockholm or the group of Tobias Heindel in Berlin. And it has also made me continue collaborating with Pascal as well. So it's an experiment that it has had a lot of very positive consequences afterwards. And I still enjoyed talking about this experiment in conferences and discussing with people about it because it's simple, it's nice, and it's rich physics.
I can understand why you chose this as one of the research projects that you're proud of. Yeah. Okay. Quantum entanglement. I need to understand a little bit of the physics here because we did cover a little bit of quantum entanglement on Under the Microscope on other episodes featuring the QuanTour heroes. So please explain to me what exactly was happening. You'd already mentioned that there were these two quick pulses and going from the ground state to the excited state. And then before coming back to the ground state, you were exciting it again to go even higher.
Yeah.
Is that the ladder thing that Doris mentioned? Did you watch Doris's episode?
Yeah,
Did you watch
it.
Doris's episode?
Similar to that, but
Okay.
even simpler.
Okay,
Even
explain,
simpler.
explain, please.
Okay, so imagine your atom.
Mm-hmm.
The first pulse brings you to the excited state. Okay,
Right.
fine. You have not emitted any photon. You just have your atom in the excited state.
From 0 to 100 for anyone who is not watching but listening. Yeah. Let's say from 0 to 100.
Exactly.
Yeah.
Then you let the atom decay, which is going to decay. The physics law oblige it, so you will be decaying.
Right.
And while it is decaying, your atom is going to be entangled with the light field in which the atom is emitting. So you will be finding your atom in a situation in which either your atom is in the excited state and has emitted 0 photons, because it has not decayed yet,
Right.
or it has decayed to the ground state, and then you have emitted one single photon. So this we write it as excited 0 plus ground 1. Okay, 0 and 1 is vacuum or single photon, and excited and ground is the state of the atom. So this composes an entangled state in which you don't know. If you know in which state your atom is, you will know how many photons it has emitted.
Correct.
This is entanglement. So while you are in this situation, you come with the next pulse. Okay, and the next pulse is going to affect the state of the atom. I repeat again, you are in the excited 0 plus ground 1. When the pulse comes, it's going to invert the status of the atom. Instead of excited 0, ground 1, you will have ground 0, excited 1.
I'm confused. Okay, explain it to me. But let's say like we have 2 tennis balls.
If I had a blackboard, I could write it.
No, we are gonna explain. We are gonna let's go with the ball because Ronaldo also in with some ball or something. The ball is in my hand. It is in the ground state, and now I throw it in the air where it will go to the excited state.
Okay. Let's put it like this. Then I was saying that the ball is at 100 and
Right.
it has emitted no light. The ball is at 0 and it has emitted 1 photon.
Right.
Then the next pulse makes the ball, the one that was at 100 goes to 0, and the
Right.
one that was at 0, it goes to 100. I just make the ball change the position in which it was. Okay? With the second pulse is affecting how the ball was, or the state of the atom, as you want
Right.
to call it. And then I'm going to let the spontaneous emission be fully completed. So the ball that is in the ground, the ball that is at 0 will remain at 0, and the ball that was at 100 will emit a single photon eventually. So what is going to happen then is that if I look at the light field mode where the light is emitted, I will find a 0, 0 plus 1, 1 state, meaning that if I measure one photon that comes first, then compulsorily there will be another photon that comes after. Or if I measure nothing in the first time being,
Yeah.
then in the second I will measure the same vacuum. Okay? So this is entanglement. It means that
Right.
if I get one photon, then I get another one. If I get one vacuum, then I will get another vacuum.
And this is important for the security part of the quantum communication, right? Because we covered that. I remember this because it is if we are communicating, and in your case it has to be like 0, then for me also it has to be 0. If it is 1, then it has to be 1, and that is how the information is stored. That's how Doris explained with the ladder and stuff.
So entanglement in general is the motor behind all the quantum applications with
Right.
light.
Right.
In our case, because we are using as encoding basis vacuum and single photon, because
Right.
we are not using, I don't want to say complicated words, but we are not using, for example, the polarization of light. We are using presence of light or absence of light.
Right.
Imagine I take one of those temporal beams, say the first one, and I want to change, after it is emitted, I want to change this single photon to be a vacuum, or vice versa. If I want the vacuum to become a single photon.
I'm already confused. Let's do it this way. Yeah, let's do it this way. Let me approach it this way. So you mentioned 2 pulses. That I understand.
Yeah.
2 pulses, ground state, excited state. That I also understand. For the emission of a single photon to happen, an atom has to go from 0, that is the ground state, to 1 to 0.
Yeah,
so
you
0, 1, 0.
Exactly. The laser puts you in the excited state,
Right,
and then the
correct.
spontaneous emission will make you emit a single photon.
Right, that I understand. So now when the atom is 0 to 1, and then when it is coming down to 0, that is when your second pulse of light hits it. Maybe it is halfway, maybe it is one way, whatsoever. And then it is excited again, so it goes to, let's say, 1.5, 1.
Yeah, you flip basically the status of the atom. So if it was in this position, you will invert it, and if it was in this one, you will invert
What
it
do you
again.
mean by inverting it? That I don't
So
understand.
it's making the ball, if the ball was in the ground state, you bring the ball up, and if it was up, the pulse brings your ball down. So if it brings it back to the ground state, it will not emit anything. This is why you will have vacuum in the end.
Oh, okay.
You
It's
can think of-
flipping the coin, yeah?
Exactly.
So if I have the ball in my hand, which is in the ground state, and then I throw it to the first floor, and then while it is coming down from the first floor to the ground floor, your second light pulse is hitting it, and then it goes from the
whatever state it was, the opposite.
the opposite. But if it is at, let's say, 0.75,
Okay, I think you are thinking there with a classical mind,
yes.
and you can't. So
Okay.
the atom cannot be in one, cannot be at 0.75.
Of course, it's not a physical ball that is going up and down, right?
It is something that is either in one state or the other.
It's either zero, it's binary. It's
Then, how much probability you will have to find the ball up or down, it will depend how much time you're waiting for the ball to decay.
correct.
When I was explaining this whole experiment, I was simplifying it, mentioning that I will wait for a time in which I have the same probability of finding my ball in the excited state or in the ground state.
Right.
But if I wait a very long time, it will be most likely to find the ball in the ground state because it will have already decayed.
Decayed, right. And only emitted one
Exactly.
photon.
Exactly. This is why here we are playing with the state of the atom, the state of the ball, up or down, I don't know where, but with the second pulse, I will rotate it and it will affect the kind of light that will be emitted afterwards. It disentangle the state.
So if the single photon is doing 0, 1, 0, and that's when you have one single photon, so in what you're mentioning, it is like 0, 1, and then when it is hit by this other light bulbs, even if it is in 1, and if it is coming down to 0, then there would be this, oh, this is so cool.
It's a bit complicated. It took me a while to catch it up when my colleague Stephen was telling us about this possible explanation. But as soon as you write it, and then it becomes quite easy to follow.
Once you understand it, then you understand it.
Yeah.
I think I understood it. Not entirely sure, but I think I understand it a bit better.
I can tell you something very cool about it.
Yes, tell me.
It is not only about 2 pulses. You can think about 10 pulses, okay? In which each pulse is then flipping and flipping and flipping the state of the atom.
Right.
Then what it comes after is a very complicated state of light. It's what we call physicists scaling the complexity of the state itself. For these 2 pulses, you generate a 0, 0 plus 1, 1. Easy. Two time beams, early and late.
Right.
If you start to put more and more pulses, always hitting before the atom has not fully decayed, the kind of state that you will generate, it scales in a very complex manner. And after looking to the maths of the problem, and this is the cool part because there is also very basic maths involved on it, we have seen that the structure of the light state that emerges, it follows the Fibonacci sequence. This is very cool because we can see that the properties of the state that we generate with these n pulses,
Yeah.
it follows this sequence. And there is also the gold number involved as well. I don't know if you know about the gold number, which is a number that emerges when you make the ratio between 2 consecutive Fibonacci numbers. So if you make divided by 2 or 5 divided by 3 or 8 divided by 5
Right.
in the series, this one, the gold number.
Yeah.
So we're at the moment I was like, but this looks like numerology, what we are doing here. It was very cool. So this is also this link to fundamental mathematics is something that I like very much about this paper.
It makes sense. Oh, wow. Okay, I'm going to have to look this all up and again understand. So we tried the ball, we tried everything, but this is really cool. I can understand why this is one of the, not just from the accidental discovery perspective, but also from the physics perspective, and also this connection with mathematics. And it just goes to show that the deeper you go in the science,
more complex it gets.
the more complex it gets, and the more fields are coming together. In this case, the physics and mathematics, which are...
It turns out, after discussing with many scientists and mathematicians as well, it turns out that the Fibonacci series is very natural. It emerges in many different topics. And it is the result of applying some recursivity in a given process. When you repeat something on something, you will turn out in the end having structures or patterns that are related to this series.
I'm curious if the number 42, which is the answer to everything,
It's-
is that
it's-
also related somewhere?
I think it does not appear. I think it does not appear in the
42
Fibonacci.
doesn't appear in the Fibonacci. Is it? No.
I don't think so.
13, then we'll have to, then it will be
21, 21 that makes after plus 13 is
33.
33,
Yeah.
and then you add it
No.
and doesn't come.
Then it is already in the 50s we are, not the 42. And I'm thinking about, this repeat, because 42 is the answer to everything. And when you said that there is, where there is repetition, there is sometimes coming this Fibonacci, or very often the Fibonacci, because it's like the nature stuff. Oh, this is really cool.
And then we can bring it even more complex. But I
Please.
don't know if you want to go there.
Please just introduce it. And if not, then I will be like, okay, Carlos, that's enough. But yeah, please introduce it. Yeah.
And this is something related to the experiments that I have been doing together in collaboration with the group of Tobias Heindel in Berlin. We came up with this idea of, instead of using a two-level system, so the ball up or down, now the ball can occupy 3 levels: second floor, first floor, and bottom ground floor.
Ground floor, yeah.
So if you do this experiment with this 3-level system,
Right.
the state that you emit per se, if you bring your ball here, you will emit one photon
One
from here
photon.
to here and another photon from here to here.
From the second floor, the first floor, 1 photon, from first floor
Yeah.
to the ground floor. Because I always have to think about the podcast listeners who only are listening to the audio. So that's why I'm explaining it.
Yeah,
Yes.
sorry, I should do it as well. So
That's fine.
you have to think that decaying from the second to the first,
Right.
it makes a photon of one given energy. And then when you emit from the first floor to the ground floor,
Mm.
you will emit a photon with a different energy, a different color.
Right.
So you have 2 photons with different colors.
Okay.
You can apply this sequential excitation with pulses so that you apply rotations on the
Mhm.
status between the atom that can be in the ground and in the second floor. And if you let your spontaneous emission occur, and then you will have more possibilities for your atom to have decayed and have emitted photons at different energies. And then you come with a second pulse. Your entanglement now is not only in time, it's also in energy.
Oh my God. Okay.
And
Okay.
then a bit more complex than that. And with that, I finish.
Yeah, please. Then we can move on to a more simple question. Yes,
yeah.
please.
One of the quantum dots that Tobias is studying in Berlin is this 3-level system. But actually, when you come to the first floor, you can be in 2 different flats. Okay.
Oh, come on. Okay.
And in order to decay from the second floor to the first floor,
Right.
if you go to flat A and flat B, you
Right.
go with different polarizations of light. Okay.
Okay.
And from flat A and flat B, when you go to the ground state, you also emit with different polarizations.
So we are actually emitting 4 photons.
It's going to be possibilities for emitting 4 photons. So if you apply then this 2-pulse excitation in this kind of system, you will end up with entanglement in polarization, energy, and time. So things get very complicated very easily. And this
Right.
is something that is very interesting, to access complexity with very low resources.
But why do you want to make it so complex? Do we actually need this for the secure communication with
Yeah, I think-
quantum?
Yeah, I think that access complexity with your hands is the hot dream of every physicist, right? You want to make things, you want to understand things that are extremely complex. This is where the forefront of knowledge lies.
Yeah, absolutely. I
So-
understand from the fundamental or the basic research or hardcore physics research perspective, this is really fascinating. But when we think about it, when I'm thinking about bringing this as like a real life application, secure quantum communication, I'm sure this will play a role.
It
right?
will eventually, but the way I like to see it is as a very complicated path in which you have to be getting different results that in the way, while you are approaching towards that quantum application, you are leading seeds of other lines of research that have consequences in the same domain.
Right, and they will bring their own applications and open more doors which we are not even aware of at this point.
So this open door to complexity might not have a super immediate, like in next year, application that we will use, but eventually it will. It has been the motto of science for forever and ever.
Yeah.
This is our job.
Absolutely. This is really great, and thank you for messing with our minds even further. This is really interesting, and it's very evident to me, Carlos, that you really love the research aspect of being a scientist. Correct me if I'm wrong here.
No, absolutely right.
You love it, right? That is so good. But what else do you like about being a scientist, especially now that you're a professor, right? There are other aspects which are going beyond the lab. So what else do you like about being a scientist?
I think that this is a very common answer for every person that you will probably discuss with, but the international aspect is very important. The possibility to travel a lot, to meet different opinions, different people, different techniques, different physics, It's a way of being in constant touch with the whole world community on the topic. I don't travel as much as maybe in the past. I still travel quite a lot, but I think it's great to know people everywhere, to be able to have a discussion about something that you both know, even though you are living in completely different continents or countries. And the second thing that drives me a lot to do research, at least at the moment, is to see that the knowledge that I have, I can pass it, and it can be greatly overcome by my students. They can do much better than what I do and bring research even farther. And this is something that is absolutely amazing when you see somebody, you explain something simple and then they can bring it much farther away. I think it's really nice, that aspect of teaching and seeing how the work of others are even better than, much better than yours.
So the international and the collaboration aspect, and also the
passing the knowledge.
intergenerational
Yeah.
sort of like passing the knowledge and like passing the baton. We have had a version of this answer that you gave, but yeah, that makes a lot of sense. That is really, it almost makes me want to go back to the research, being an active scientist. And Carlos, speaking about the research as a research experience as a whole, I hope your research experience has been wonderful. So far, it sounds wonderful, but of course, we have
Ups and downs, of course, but
Of course, but if you had 3 wishes to improve your research experience, what would you ask for? And I'm not promising anything here.
okay. To improve my research at the moment, or to have improved my research in the past?
At the moment.
At the
You
moment,
can't go back in the past, right? That is, we are not there yet. But right now, I can't go back in the past and change, because then we won't be sitting here, right?
Yeah.
So
I think that one aspect that is common to most of research everywhere in the world, I think that we have a lot of administration tasks that are not very intelligent and that we still have to comply with
right.
if we want to continue having a functional activity. So reporting, when you come back from a trip, doing all the bureaucratic work, before doing the trip, doing as well a lot of bureaucratic work, different responsibilities that we have in the faculty, or meetings that might not be as useful as we would like to. This is one thing that I know I cannot improve, but still I would love to mention it. What else? Of course, I could be asking for infinite amount of money
Of course.
for my research.
Funding, of
It's
course.
like playing a video game with all the codes, no? Unfortunately, it's not possible, at least not in Spain.
We are not talking about the possibilities or not. We are just putting out the wishes. That's all we are doing at this point.
And then if I could ask for something more realistic, I think it would be fantastic for my research to have a very good coffee machine. That would be
No,
very,
that
very
is
nice.
realistic.
That is realistic. You saw the coffee machine in my lab. It's not that good. Huh?
No, also there is no coffee machine in the lab. There is no coffee machine in the lab, okay? In the lab, there is no food or drinks or anything.
I just killed all the possibilities to have PhD students in my lab. If they know,
But now that you have put out there, let's just put like, which coffee machine do you want? Maybe that brand person is watching and maybe we can get the coffee machine for
so
you.
Jura coffee machines.
Jura
please.
coffee machine.
You can sponsor the research activity in my lab and also supply with 100 kilo of coffee grains per year. That would be amazing. Thank you.
At least 100. Yes. Jura coffee machine. I will pass on the message so that you get the coffee.
Okay.
And the coffee machine and the different blends and
Um,
fueling research, quantum communication
caffeine.
research.
Yeah.
Yeah, with caffeine is very important. Yeah, but like the bureaucracy that you mentioned, definitely. This is something that also Armando, I mean, almost everyone talks about that.
And myself, I am at a much lower position than Armando or Rinaldo, so I cannot complain as much. I guess that they have way higher responsibilities.
True.
From the moment you start to hold certain positions within the institute, or if you collaborate with the ministry or things like that. I'm not there yet, so I should not complain.
Not yet, but soon. Hopefully soon.
Let's see.
Let's see. But yeah, bureaucracy in general, I think that is in science, I feel like in research specifically, we don't really talk a lot about the burden of bureaucracy and how it slows everything down. If anyone from the system perspective, if you're
I don't know.
watching, please help scientists, save them from all the bureaucracy. Because also it's not that universal, right? It's not even Europe-wide the same. You might have a
It depends from
bureaucracy-
country to country. I
Right.
would like, my experience in Germany was reasonably good. I don't know my German colleagues now, they're going to say,
Yeah,
what
because
are you
you
saying,
didn't-
Carlos?
Exactly. I live in Germany and no.
I don't know which country could be worse. I think that Spain keeps quite high in the rank, I would say.
Ah, okay.
But I don't know if I have to compete with France or Italy, maybe there it's even worse.
Yeah,
It could be
maybe.
the case. I have my colleagues from the CNRS complaining very recently and telling me the complexities that they have Italy, probably it's also a maze of different paths to get to complete your administrative tasks. I don't know.
Yeah. It's just
Scary.
It is. It is. It definitely is. So anyone watching, if you have answers and help, this could be a business opportunity also. I feel like that, okay, we will take care of all the bureaucracy
Wow.
for you, and let me explore that and get back to you on that. And unlimited funding, I mean, that is like that's a very realistic wish, I would say.
No, not very.
It's more realistic than a bureaucracy thing.
Probably. If you put it like that, in those terms. Yeah, no, but we do our best to try to gather all the funds that we need in order to continue the group running and getting new equipment and hiring new people.
Yeah, absolutely. And Yura, please sponsor the coffee for Carlos's group. You will have a lot of happy scientists.
We
Your
will
brand
acknowledge-
ambassador.
And we will acknowledge in the paper. Thank you. We
Everywhere.
acknowledge Yura for providing very important support along the work of this project.
It's very important. Yes, absolutely. No, seriously, this is very important. I will pass on your message. Perfect. Carlos, this has been wonderful. Learning about your journey, your research, also the different projects that you're involved in.
Thank you very much.
Your wishes, which I hope I can make them come true, at least the last one with the coffee machine. But before I let you go, I have to ask you one last question. So in addition to featuring on Under the Microscope podcast, you will also get the keys to the Real Scientist Nano Twitter account
Yeah, true.
or X account for one entire week from Monday to Sunday.
Mhm.
That account has more than 3,400 followers. No pressure. What can the followers expect when you're tweeting from this account?
I was thinking of providing some insight on what it is my work in the university, what is the kind of the interactions that I have with the members of my group, and also why not something about the lifestyle here in Madrid. I would like to remind that Madrid is a wonderful city to live, and I think it's one of the assets to foster through the window that you are allowing me to use. So maybe for some potential students, it would be nice to see what it's like to be here in Madrid, to be here in the Autónoma, and maybe they will find this place like a very nice academic house to develop their career. That would be basically my idea for the next account.
Right, and also the suitcase.
Of course, yeah. I mean,
The QuanTour project.
we earn it, working hard. You will get soon this G2 second order correlation function measured in our lab.
Okay, brilliant. And also some events that you are organizing. I think you had mentioned
True.
that would also be good to have, no?
Yeah. Thank you very much for reminding me. Well, we will be organizing this kickoff meeting the 6th of September here with all the partners of this QuanTour project. It would be great to welcome them here. And then we will be organizing an international school on quantum photonic technologies that will be happening the first week of September 2025.
25, so that is in next
Yeah.
year, so 15 months from now.
I'm co-organizing this school with Professor Luis Viña, that is a very well-known professor in this university,
Right.
within the Institute Nicolás Cabrera. It's a material science institute, also affiliated here to the Autonomous University of Madrid. And our idea is to bring the best names in quantum photonics in different platforms. So for communication, for computation, sensing, metrology. And also I had the idea, and I think it's probably very interesting to bring companies
Yes.
that are working at the moment, or startups that are working at the moment in the topic, so that the attendees, PhDs and postdoc, potentially, they will have this double vision of what is happening at the moment in the forefront of academia, and also having a view on what it is happening as well at the industry level.
Right.
I hope that the formula is going to work, and we will see how it's going in the organization. We are starting just now to call the people and try to see what is the availability of all the big names to come to Madrid. It's going to be in the Sierra, in the mountains of Madrid.
Ooh, right. And you maybe like 1,000, 5,000 students, or
It's
is
quite-
it like just limited seats only?
It's going to be a bit of a petit comité, so to say. I don't know what is the limiting number of assistants, but I would say that it's between 50 and 70 or something like that.
Right. It will be very competitive. So
I don't know what
To
is going
get
to
in.
be in the end the reception of it, but I understand that next year being the International Year of Quantum Technologies and Sciences, I guess it's going to have a very big impact, and we are going to do our best as well to make of it something that where people want to be. So let's see how it
Right.
goes.
Not just from the science perspective, but also from the location perspective,
As
because
well.
September is also a great time to be
The
here in the
best.
mountains.
I mean, there is springtime and the late summer, beginning of autumn, where Madrid is fantastic.
That's wonderful.
So-
That sounds great. That sounds great. Looking forward to having you on Real Scientist Nano. Lots of pictures from the campus, from the lab, from life in Madrid, and also everything else that you mentioned with so many different events that you have upcoming, and of course, QuanTour. We want content and we want to see everything with QuanTour. So thank you very much, Carlos. This has been wonderful and excited to have you on Real Scientist Nano as well.
Thank you very much for having me. I mean, it was my pleasure. And well, looking forward to the next things that will happen in the context of the QuanTour.